So on root locus, problem number 1. The given system is g of s h of s is equal to k divided by s into s plus 3 s plus 5. Draw the root locus. Determine for damping ratio equals 0.6. Closed loop dominant poles, damp, natural frequency and gain k. So for the solution, first we take the considered system, that is g of s h of s is equal to k divided by s into s plus 3 s plus 5. Step 1. So in the denominator there are three poles, that is s is equal to 0, s is equal to minus 3, s is equal to minus 5, and in the numerator there are no s terms, so the number of zeros is 0. So since number of pole is greater than number of zeros, the number of branches will be equivalent to pole, so it is 3, and p minus z is equal to 3, that is 3 minus 0. So 3 branches approaches infinity. The starting point is from the branches will move from pole to infinite. So the first pole is 0, 0 to infinity. The second pole is minus 3, minus 3 to infinity. And the third pole is 5 and minus 5 to infinity. Step 2. Selection of real axis. One breakpoint exists between s is equal to 0 and s is equal to minus a. Let us see. So in the previous case we have found out how many poles and zeros are there in the system. So the number of poles were 3 and there were no zeros. And the poles number were at placed at 0, minus 3 and minus 5. Now first we need to decide where the root locus exists. So let me keep the cursor point at this point, and to the right side of this cursor point there is only one pole which is odd number. That means root locus exists at this point. So root locus exists from 0 to minus 3. Now if I keep the cursor at this point, to the right side of the cursor there are two poles which is an even number, so there is no root locus exists between minus 3 and minus 4. So if I keep the cursor at this point, to the right side of the cursor there are three root locus which is an odd number, or three poles which is an odd number, so the root locus exists. So from now, where does the breakaway point exist? Just by observation we can say that between two poles there exists a breakaway point. The step 3 is angle of asymptotes. So we know the formula is theta is equal to 2q plus 1 into 180 degree divided by p minus z, where q is equal to 0, 1, 2, 3. Since there are three branches, so there will be three angles. So if I substitute for q is equal to 0, I get answer as 60 degree. If I substitute q as 1, I get answer as 180 degree. If I substitute q is equal to 2, I get theta 3 value as 300 degree. Step 4, centroid. So we are only concentrating on the real parts. So sigma is equal to summation real parts of the poles g of s h of s minus summation real parts of the zeros g of s into h of s. So in real part poles we had three poles, one at 0, one at minus 3 and one at minus 5. We simply need to add all the things. There were no zeros, that's why it is answer is 0, divided by p minus z. The number of poles were 3 and zeros were 0, so it is 3 minus 0, it is 3. So the final answer we get is minus 2.667 for the centroid. So at this point we need to draw the angle of asymptotes, that is 60 degree, 180 degree and 300 degree that we obtained in the last slide. Step 5, breakaway points. So we just need to write the form in the castic equation to obtain the breakaway point. So it is 1 plus g of s into h of s is the castic equation, that is equal to 1 plus g of s into h of s is nothing but k divided by s into s plus 3 s plus 5. So if I rearrange this equation, we get in this form, that is s cube plus 8s square plus 15s plus k is equal to 0. And let me rearrange the value of k. So k is equal to minus s cube minus 8s square minus 15s. Now if we need to differentiate this value, so dk by ds is nothing but minus 3s square, 8 to the 16, so it is minus 16s, and s term will get cancelled because we are differentiating this, so it is minus 15, which is equal to 0. Now, since it's a quadratic equation, we can easily solve the quadratic equation to get two roots because the order of s is 2. So s1 is equal to minus 1.2137 and the other value is minus 4.119. So thus s is equal to minus 1.213 is a valid breakaway point. Why? Because in this part the root locus exists, but in minus 4.119 there is no root locus exist. So by using the equation again, we consider this equation number 1 and we substitute the value of s in this. So we get the k value, and the k value is plus 10.2837 at breakaway point. Step 6, intersection with imaginary axis. We just need to calculate the characteristic equation that we obtained in the last slide, and we write the characteristic equation in the column based structure. So it is s cube, s square, s1 and s0, and we take the alternate coefficient, that is 1 and 15, and we write in a row wise. Again we take 8 and k, we write it in the row wise. To solve this further, it is nothing but 8 into 15, that is 120, minus 1 into k divided by 8. We got this. Next value is nothing but, we have zeros here, so it is 8 into 0, again 1 into 0 divided by 8. We get the answer as 0. To solve further, we have this, that is 120 minus k divided by 8 into k, again 8 into 0 divided by the same term, that is 120 minus k divided by 8. So the value we get is k. Now for the system to be marginally stable, so we are only concentrating on the stability part. We know that the row should be zeros. If we have two zeros in the row, then we can say that the system is marginally stable. Under what condition we get a zero at this point? When k is equal to 120, we get this row to be completely zero. The next is, we need to find the value of s when system is marginally stable. So we just need to take the previous row and we can write 8 s square plus k is equal to 0, and we know the value of k, that is 120. We get the value of s as plus or minus j 3.873. So intersection with imaginary axis we obtained for marginally stable condition. Step number 7, no complex poles of 0, hence this step is not required. So in the problem, in the given system, there are no complex poles or zeros, that's why there is no need to do this step. In the problem, they are given the damping ratio as 0.6. For this value, we need to find the closed loop dominant poles and the characteristic equations. So this can be obtained by drawing a line at an angle theta equals cos inverse zeta, that is zeta value is given as 0.6. So cos inverse zeta, when we draw a line at this angle, we get a interaction in root locus, and that value is minus 1 plus j 1.25, and this is the dominant closed loop poles. So we get minus 1 plus j 1.25. If I write a characteristic equation for this, there are two roots to this. One is minus 1 plus j 1.25 and the other one is minus 1 minus j 1.25. So the characteristic equation obtained will be s square plus 2s plus 2.5625 is equal to 0. So this is in the standard form of a second order system. So we can easily compare with s square plus 2 zeta omega n s plus omega n square. In the place of omega n square, we have 2.5625. So what is omega n? Omega n is 1.6 rad per second. So the next thing is, we need to find the value of zeta. To obtain the value of zeta, we can use magnitude condition. In magnitude condition is nothing but g of s h of s is equal to 1. In our case, the given equation is k divided by s into s plus 3 s plus 5, and at s is equal to the dominant poles obtained, that is minus 1 plus j 1.25. So the value of k that we obtain when we substitute this value, s is equal to minus 1 plus j 1.25 in this place, that is in place of s, then we get obtained is k is equal to 15.8142. The last step, step 8, draw the root locus. So we take the graph sheet. First we will sign the axis. X-axis is the real axis and y-axis is the imaginary axis, and we have some pole points, that is from minus to minus 5, which will go along till infinity. So in the given system, the number of poles given is 3, that is one is at 0 and the other is at minus 3 and the other one is at minus 5. The first thing that we need to do is we need to find where the root locus exists. So if I keep the cursor at this point towards the right, there is only one pole which is odd, so the root locus exists from 0 to -3. Similarly, if I keep the cursor at this point to the right side, there are two poles which is even number, so there will be no root locus exist between -3 and -5. And finally, if I keep the cursor at this point to the right side of the cursor, there are three root locus. There are three poles, so it is an odd number, so the root locus exists at this point. There are no zeros in the given system, so we are not concentrating on zeros. So the first thing is we are finding the centroid. To find the centroid, we already gone through the formula, that is summation of poles minus summation of zeros divided by p minus z. We got the values as -2.667. From this centroid, we need to draw the asymptotes angles. So the angles we obtained were three angles because branches were three. So the first angle was 60 degree, second angle was 180 degree, and the third angle was 300 degree. Next point is we need to search for the breakaway points. So from the diagram, we have calculated that we got two breakaway points. One was at -1.2137 and the other one was -4 point something. So as you can see from the diagram, in from -3 to -4 there is no root locus. So we have not considered the value -4.156 as the breakaway point, but instead we have considered the breakaway point to exist at this point because the root locus exists from 0 to -3. So the next thing is we need to see that how the value will cross the imaginary axis, that is the for marginal stability, and we found the values by Routh's array that it is -j 3.87 and +j 3.87. So we need to draw the curve from going along with the breakaway point towards infinity. Now this line we are drawing in this fashion. Why? Because this is written with respect to the asymptotes. So it should be in the same parallel lines with respect to 60 degree. Again in the downside it should be parallel with respect to 300 and it should move along the imaginary axis at +j 3.87. Again -j 3.87. Now by using cos theta, that is they have given the zeta value as 0.6, and if we substitute zeta as 0.6, the angle is 53.13 degree. So for 53.13 degree we just need to draw a line and we get a point P on this line, and this point P is the dominant poles, and this dominant pole is nothing but -1 plus j 1.25. So we are finding the root locus by drawing this, and the line intersect locus at point -1 plus j 1.25. Problem number 2. The feedback control system has an open loop transfer function g of s h of s is equal to k divided by s into s plus 3 s square plus 2s plus 2. Draw the root locus as k varies from 0 to -infinity. So in this given problem we have a complex conjugate. Since we have a complex conjugate, we have to use step number 7. So first thing, the solution is, first we'll know how many poles are there, how many zeros are there, which is dominating, either pole or zeros, or how many branches are moving towards infinity. Since there are no zeros, it indicates that whichever the poles exist, it will move towards infinity. So step 1, p is equal to 4. There are 4 poles, s is equal to 0, s is equal to -3. Since the order of s in the quadratic equation is 2, there is two more roots will be there. So totally there are 4 poles. There are no zeros, so z is equal to 0. And since poles are greater than zeros, I can write number of branches is 4, which is pole, and p minus z is equal to 4. So there are totally 4 branches, and all 4 branches will move towards infinity because there are no zeros in the system. If there is one zero, then only one branch will move towards zeros, and the other 3 branches will move towards infinity. Now the starting point. So we have s is equal to 0, -3, -1, plus or minus j. The terminating point are all are at infinity. Step 2, we'll write the partial root locus, and there are two axes, x-axis is real axis and y-axis is imaginary axis, and in the given system there are 3 poles in total, one pole at 0, another pole at minus 3, and there is one conjugate poles which has two roots, that is minus 1 plus j and minus 1 minus j. So first thing is we need to calculate where the root locus exists. So if I keep the cursor at this point, towards the right of the cursor there is only one pole, hence since it's an odd number, the root locus exists from 0 to minus 3, since we are neglecting the complex conjugate for the count. So if I keep the cursor at this point towards the right side, there are only two poles after neglecting the complex conjugate, that are these are minus 3 pole and pole at 0. So there will be no root locus from minus 3 to minus infinity. Step 3. Angle of asymptotes. Theta is equal to 2q plus 1 into 180 degree divided by p minus z, where q varies from 0, 1, 2, 3. Since there are four branches, so we get four angles, asymptotes angles. So when I substitute q is equal to 0, angle obtained is 45 degree. When I substitute q is equal to 1, angle obtained is 135 degree. When I substitute q is equal to 2, the angle obtained is 225 degree. When I substitute q is equal to 3, the angle obtained is 315 degree. The next thing is we need to find the centroid. To find the centroid, we are only concentrating on the real part of the zeros and poles. So summation of real part of open loop poles minus summation of real part of open loop zeros divided by p minus z. So in open loop poles we have 0, minus 3, and we have two conjugates, that is at minus 1. So we need to write twice. So we have minus 1 and minus 1. And since there are no zeros in the system, we are taking it as 0 divided by p minus z. P minus z. So the number of poles is 4 and number of zeros are 0. So we get the final answer as 4. If we solve the centroid value, the final answer we get for centroid is minus 1.25. Step 5. For the breakaway points, we consider the characteristic equation, that is 1 plus g of s into h of s, that is 1 plus given system equated to 0. We can rearrange this equation in form of s to the power of 4 plus 5s cube plus 8s square plus 6s plus k is equal to 0. Now we write everything in terms of k as per the steps. So k is equal to minus s to the power of 4 minus 5s cube minus 8s square minus 6s. Now we differentiate it with respect to s. So the answer we get is minus 5s cube minus 15s square minus 16s minus 6 is equal to 0. Finally, we write everything in terms of positive values, so equated to 0. That is 4s cube plus 15s square plus 16s plus 6 is equal to 0. Now, from the given equation that obtained is a power of cube. If it was a quadratic equation, we can easily solve this. Since it's a power of cube, it is in the examination, it is best to use calculator in polynomial mode with the order of 3. And by solving that, we get the values as s is equal to minus 2.288 is the breakaway point. Why? Because in this value the root locus exists. The other two roots are complex conjugate with real part minus 0.7307 and cannot be a breakaway point, because at that point of time, one is it is a complex conjugate, the second thing is there is no root locus exist in that value. So from equation 2 we substitute the value s is equal to minus 2.288. The value of k obtained is plus 4.3315. Step 6. Intersection with imaginary axis. We consider the characteristic equation given, that is s to the power of 4 plus 5s cube plus 8s square plus 6s plus k is equal to 0. We write this characteristic equation in a column wise manner, starting from the higher order to the lower order, that is s to the power of 4 to the s to the power of 0. We alternatively take the coefficient of s to the power of 4 and we write that in terms of a row wise, that is we take 1, next is 8, next is k. In the second row for s cube we take 5, 6 and 0. To solve roots array, the formula is simple. It is 5 into 8 minus 1 into 6 divided by 5. The answer obtained will be 6.8. Similarly, we multiply 5 into k minus 1 into 0 divided by 5. The answer we get is k. For the next row, it is 6.8 into 6, which is 40.8, minus 5 into k divided by the same value, that is 6.8. For this value to be obtained, we multiply 6.8 into 0 minus 5 into 0 divided by 6.8. The answer we get is 0 only. For s to the power of 0, we multiply 40.8 minus 5k divided by 6.8 into k minus 6.8 into 0 divided by 40.8 minus 5k divided by 6.8k. So since in the numerator and the denominator we have the same value, we are left out with only k. So k will be the answer for S naught. Now to find how good is the system, marginally stable, we need to know what is the limit of k. First thing is the k value should be always greater than 0. So here first we take the consideration of s to the power of 1, that is 40.8 minus 5k. So what will be the k margin? K margin will be 8.16. That means if I substitute 8.16 to this row, the answer I get is 40.8. So 40.8 minus 40.8 is 0. So this whole row becomes 0. For any system, when the whole row becomes 0, it indicates that it is marginally stable. Just for the calculation purpose, we continue with the system. Now here we find A of S, that is the auxiliary equation. Auxiliary equation can be obtained just one row above this, that is S square. I can take 6.8 S square plus K is equal to 0. We already know the value of K, that is 8.16. If I substitute the 8.16 in this equation, the value of S we obtained is plus or minus J 1.095. So this is the point in the imaginary axis that these breakaway points are moving along. Step 7, angle of departure. To find angle of departure, first we draw all the lines from the pole to this point, that is the complex conjugate pole -1 plus j. So the first line we are drawing making an angle of 5p1. The second line when we draw to this pole, it makes an angle 5p2. The third line when we draw, it makes an angle 5p3. So 5p1 is nothing but 180 degree minus tan inverse of 1 divided by 1, that is opposite by adjacent. We get 135 degree. 5p2, as you can see, it is exactly 90 degree here. So there is no need of any calculation. 5p3 is equal to tan inverse 1 by 2. So the angle made is 26.56. So what is summation 5p? Summation 5p is nothing but the addition of all the angles. So we get 251.56 degrees. Since in the problem we don't have any zeros and we are not finding any angle of arrival, phi z will be equal to 0. So what is phi? Phi is nothing but summation 5p minus summation phi z is equal to 251.56. The angle of departure is given as 180 degree minus phi. So 180 degree minus 251.56, we get the angle of departure. So in this case, the angle of departure from this complex pole, that is -1 plus j, is minus 71.56. Now again, at the other end of the pole, that is -1 minus j, the angle of departure is 71.56. Now step 8, the complete root locus. We already have all the details required to construct the root locus. First thing is we will take the axis, real axis and imaginary axis. We keep the scale 1 unit, 2 units is equal to 1 in both the axes. Then we represent all the poles on the plane. We have totally 3 poles, 2 real poles and 1 complex conjugate poles, in total 4 poles. Now it is represented like this. Next we will find the root locus existence. The root locus exists from 0 to -3, that is from this point to this point, and from -3 to infinity there is no root locus. And we know that by the calculation from 0 to -3 there is a breakaway point. So the breakaway point calculated is s is equal to -2.28. And the next thing is we need to find the centroid. Centroid found is s is equal to -1.25. Centroid is nothing but the summation of real pole minus summation of real zeros divided by p minus z. Next is we need to add the asymptotes angles. So one asymptote angle is at 45 degree, the next asymptote angle is at 135 degree, the next is at 225 degree, and the last one is at 315 degree. Next we need to draw a curve passing through the breakaway point going towards infinity. As this breakaway point is between two poles, the direction of the curve is in this direction. Instead of this, if there was 0, then the direction of the arrow mark would be in reverse. The next thing is we have already calculated the angle at which it touches the imaginary axis, that is plus j 1.09, and the angle of departure, since it's a complex conjugate, we need to find the angle of departure. So angle of departure obtained was minus 71.56. Now how do we write this? First thing that you need to do is you need to draw a line horizontally to plus j. After that, from this we need to create an angle that is minus 71.56 in this order, like this. Then we need to draw a curve and it has to move along the asymptotes going towards infinity. Again, in the bottom side we need to do the same thing. Again, we will draw a line, create an angle exactly 71.56 degree. Then we create this curve and move along with minus 1.09 j, and it will go towards infinity. Now here, as you can see, there were 4 branches going towards infinity. As you can see here, this is one moving towards infinity. Again there is one more branch moving here towards infinity. Again here there is one more branch moving towards infinity. Again in the complex conjugate there is one more branch moving towards infinity. So whatever we discussed for this problem, we have represented it properly. And the last one is k marginal. At what point it will be stable? Beyond this it becomes unstability. So k marginal is equal to 8.16. Problem number 3. G of s h of s is equal to k into s plus 1 divided by s into s minus 1 s square plus 5s plus 20. Sketch the complete root locus with approximate indication of breakaway points. Comment on the stability. Now, in the given problem, the moment you see s minus 1, it indicates that s is equal to 1 and it comes on the right side of the axis. So, in the root locus, it is somewhat unstable, but there are term k which can make the system stable. Now, let us see by drawing the root locus. Step 1, let us understand how many poles are there, how many zeros are there. So number of poles is 4. Why? Because s is equal to 0, s is equal to plus 1. There are two complex conjugate in this, so totally there are 4 poles. Now z is equal to 1. In the numerator I have s plus 1 which is equated to 0, then s is equal to minus 1. So there is 1 0. Since number of pole is greater than number of zeros, so number of branches will be equivalent to number of poles, that is p is equal to 4. Now p minus z, p is equal to 4, z is 1, so p minus z is 3 branches. So 3 branches will approach infinity. What about the other branch? The other branch will approach 0. Now starting points are s is equal to 0, 1, minus 2.5 plus j, 3.708 because it's a complex conjugate. Now terminating points for 0 is minus 1, and for 1 minus 2.5 plus j 3.708 is infinity. Step 2, let us draw pole 0 plot. Now the total number of poles are 4. So first pole is at plus 1, the second pole is at 0. There is one more complex conjugate pole which is at minus 2.5 with plus j 3.708 and minus j 3.708, and there is one 0 which is placed at minus 1. Now let us see where there is root locus exists or where there is no root locus. Now if I keep the cursor at this point, to the right side of the cursor there are no poles and no zeros. That means it is a no root locus zone. Now if I keep the cursor at this point, towards the right of the cursor there is a pole which is an odd number, so root locus exists from plus 1 to 0. Now if I keep the cursor at this point, to the right side of this there are two poles which is an even number, so there is no root locus exist from 0 to -1. Again, if I keep the cursor at this point, there are two poles and one zero. So total is odd, which is 3. So root locus exists. It exists from -1 to minus infinity. And one more important thing that you need to observe is the breakaway point. As we saw earlier problems, that whenever there are two poles, we are sure that there will be one breakaway point here. But in our case, there is one more breakaway point exists at between -1 and infinity, minus infinity. Why is that? Because in zeros, there will be a breakaway point coming from infinity and reaching towards -1, and one more which will go towards minus infinity. Now angle of asymptotes. The formula is theta is equal to 2q plus 1 into 180 degree divided by p minus z, where q is equal to 0, 1, 2. As number of branches is 3, so we'll have 3 asymptotes angle. So theta 1 is equal to 60 degree, theta 2 equals 180 degree, and theta 3 is equal to 300 degree. Now centroid. Step 4, we need to write the concentrate on the real parts of open loop poles minus real part of open loop zeros divided by p minus z. Which are the real parts of open loop poles? We have 0, plus 1, minus 2.5 and minus 2.5. Why we are writing this twice? Because there are two complex conjugate poles. So we need to take the real part twice. Minus and minus of 1. Why? Because there is one 0 which is value is -1, and in the formula we have minus sign, so it becomes plus, divided by total number of branches, that is p minus z. We have p is equal to 4 and z is equal to 1, so it is 3. So totally we get answer as -1. Step 5, breakaway points. From the point of observation, we come to know that there exist two breakaway points. Now let us check them. So we have 1 plus g of s, h of s is equal to 1 plus k into s plus 1 divided by s into s minus 1, s square plus 5s plus 20, which is nothing but a characteristic equation. When we rearrange this, we get s to the power of 4 plus 4s cube plus 15s square minus 20s plus k into s plus 1 is equal to 0. K is equal to, let us rearrange this in terms of k. So it is minus s to the power of 4 minus 4s cube minus 15s square plus 20s divided by s plus 1. Now how can I solve this? I can solve this by division rule, by differentiating. So it is dk by ds is equal to v u dash minus u v dash divided by v square is equal to 0. That means we are keeping s plus 1 as it is, then we are differentiating this numerator equation, then we are subtracting it, then we keep this numerator equation as it is, then we differentiate s plus 1. So the final answer we get is s to the 4 power of 4 plus 4s cube plus 9s square plus 10s minus 6.667 is equal to 0. So we can use the calculator to solve this equation, or we can use factorial method to divide. Then the roots of equation we get is s is equal to plus 0.447 and s is equal to minus 2.45. As you can see, one root is at the right side and the other root is at after minus 2.45. That means there exist two breakaway points. Now other two roots are complex conjugate and are not valid breakaway point. This can be confirmed by angle condition. That is, if we solve for angle condition, we should get 180 degree plus or minus. But if we don't, but in a complex conjugate, we will never get plus or minus 180 degree. Now for s is equal to plus 0.447, when we substitute this value in the equation, that is k equation, we get the value k as 3.833. When we substitute s is equal to minus 2.45, the value of k is 80.16. Now step 6, intersection with imaginary axis. We consider the same characteristic equation. With the help of roots array, we try to solve this. That is, we consider s to the power of 4 and we move along towards s to the power of 0. For s to the power of 4, the coefficient is 1. For s square, the coefficient is 15. For coefficient of k, s to the power of 0 is k. Similarly, we write for s cube, it is 4, k minus 20 and 0. How we are solving this? It is in the same principle, that is 4 into 15 minus 1 into k minus 20 divided by 4. We get 80 minus k divided by 4. Again we go further. that is 4 into k 1 into 0 divided by 4. So the answer is 4, and the final value will be 0 since in this place it is 0. Now the next it is 80 minus k divided by 4 into k minus 20 minus 4 into k divided by 80 minus k divided by 4. So we get this answer. In the next value we get 0 answer. Again we continue like this. The final answer for s to the power of 0 we get k. Now first thing that we need to do is we need to find the value of k. Now from 80 minus k divided by 4, if we take this equation, I know that the value of k is 80. Okay, and this value of k should be less than 80. Now in the s to the power of 1, when we consider this equation and equate it to 0, this whole term is 0. So what is left out? The left out is 80 minus k divided by 4, k minus 20 minus 4k is equal to 0. So when I solve this, I get a quadratic equation which says k square minus 84k plus 1600 is equal to 0. So when I use the formula, the values that I get is one is 54.8 and the other value is 29.19. Now when you observe this, the value of k should be less than 80 and the values that I got are two values, one is 54.8 and 29.19, which is less than 80. As both the values are less than 80, it's valid. So this means the root intersects twice with the imaginary axis. This is a very important thing. And one more important thing is that when I substitute the value of k as 54.8, I get a marginally stable system. Again, when I substitute 29.19, I get again a marginally stable system. So if k marginals is equal to 29.19, the values that I get for s is plus or minus j 1.515. So this is the value that it has to cross and move towards infinity. Again, the other value is plus or minus j 2.94. So this is another value of intersection that has to cross from the breakaway point. Step 7. Angle of departure from complex pole. Now let us consider a complex pole at minus 2.5 plus j 3.708. To find the angle of departure, we need to find the individual angles, that is summation phi p and summation phi z. Now let us draw a line from the pole 1 plus 1 and the angle made is phi p1, and what we are interested in is this angle phi pm. To get this, we know that the total angle made by this line is 180 degree. This line is 180 degree. So it is 180 degree minus tan inverse of 3.708 divided by 3.5. What is 3.708? 3.708 is this value, which is the opposite value, and divided by 3.5. So from this point to this point, the value is 3.5. That is the adjacent value. So we can easily find phi p1 value as 180 degree minus tan inverse 3.708 divided by 3.5, which will come to 130.79 degree. Next, we need to draw a line from pole 0 to the same complex pole. The angle made is phi p2. To obtain it, we use the same formula, that is 180 degree minus tan inverse of 3.708 divided by 2.5. Next, we need to find the value of phi p3. Phi p3 value, the moment you see it, it is nothing but 90 degree. We just draw 90 degree. Next is phi z1. Phi z1 is nothing but the zero angle. When we draw a line from this point to the pole, it is nothing but 180 degree minus tan inverse of 3.708, that is opposite value, divided by 1.5, which is equal to 112.02 degree. And what is the value of phi? Phi is nothing but summation of all the poles angle minus summation of all the zero angles, or summation of all the pole angles are nothing but these values, 90 plus 123.98 plus 130.79. and the summation of 5z, there is only one zero pole, that is 5z1, so that value is 112.02. So we get the value as 232.75, but we are interested in angle of departure. Angle of departure formula is 180 degree minus 5. 180 degree minus 232.75 degree, we get the value as 52.75, and the sign is negative. And for what we have found out, we have found out this value for the upper pole, that is minus 2.5 plus j 3.708, and we can write the same angle to this pole with a different positive angle. Instead of minus 52.75 degree, we'll be writing plus 52.75 degree at minus 2.5 minus j 3.708. Step 8. Since we know all the information related to the given problem and we have found all the details, now we can draw the root locus. First, we consider the real axis and the imaginary axis, and we represent all the poles and zeros given in the problem. So there are four poles and one zeros. One pole at plus 1, 0, minus 1 is, this is 0, and there is a one complex conjugate poles. So first we'll find the root locus existence. Now as we know, the root locus exists between plus 1 and 0, and the root locus exists from minus 1 to minus infinity, that is from 0 to infinity. And there no root locus exists between 0 and minus 1, and no root locus exists between to the right side of the plane. So first we'll find the breakaway points. As you can see, by observation we already decided that there are two breakaway points, and by calculation we got two values, that is s is equal to minus 2.45 and s is equal to plus 0.447. As you can see, s is equal to plus 0.447 exists on root locus. That means there is a breakaway point at this point. Now whereas in this case s is equal to minus 2.45, again there it lies on root locus existence. So this is also a breakaway point. And we will find the centroid. The centroid found was s is equal to minus 1. After finding the centroid, we will draw all the azimuthos angle. Since the branches were 3, so we will have 3 azimuthos angle. So one azimuthos angle is at theta 1 equals 60 degree, theta 2 is equal to 180 degree, and theta 3 is equal to 300 degree. Now we try to draw a curve from the breakaway point. As you can observe from this, the root locus, the line will always move from a pole to a infinity or a pole to the 0. Now this is a very good example of that. The curve drawn is moving towards, one is moving towards 0 and the other is moving towards infinity. Next we'll draw one more curve, and we have calculated two marginally stable condition. That is, let us assume that the line, since it is two poles and there is a breakaway point, and the breakaway point will start like this in opposite directions. Now let us consider only the upper part of it, and the lower part will be simply a symmetry with the upper part or the replica of the upper part. So let us assume that this line is moving like this, and we have found out three lines. The first one was when k is equal to 29.19, which is less than 80, the line crosses to the imaginary axis. That is a condition for marginal stability, and the value was plus j 1.515. And as it moves along, it goes and crosses one more line, that is at k is equal to 54 0.8, and the value was plus j 2.94. Under these two conditions, one row of s to the power of 1 was 0, which was a condition for marginal stability. And once we draw this, the other part, that the downward part, is simply a symmetry. It should be in the symmetry of the upper part or just a replica of the upper part. Now the complete stable region are these two regions, that is Why it is stable? Because this part is towards the left side of the S-plane. And this breakaway point, why it is unstable? Because this breakaway point is towards the right side of the S-plane. And why these 2 points are marginally stable? Because it is lying on the y-axis or the imaginary axis. Now let us consider the final step, that is a conclusion, and comment on stability. If K lies between 0 to 29.19, which is roots are lying at right side of the S-plane, then the system is unstable. Again, if it is K is greater than 54.8, which two roots are lying at right hand side of the system, then the system is unstable. If K marginal, that is the value is 29.19 or 54.8, then we can say it is marginally stable. Now if this value K value lies between 29.19 and 54.8 and all roots are left half of S-plane, the system is completely stable. So by conclusion, we draw root locus for purpose of knowing the system, given system stability condition. Is it completely unstable? Is it marginally stable? Is it completely stable or not? If the system is unstable, then we can add zeros and poles so that we can bring the system from instability to stability.